Stay tuned and watch this basic tutorial. How to train and evaluate the latest YOLO model YOLOv11 on a custom dataset using the powerful RTX 4090 GPU. Hello everyone, I'm Constantin. Welcome back to my channel. I'm so glad to have you here as we dive into another exciting topic in the world of AI and deep learning. If you haven't seen my previous posts, I highly recommend checking them out. They provide an excellent overview of my work so far, including insights and hands-on experiments with some of the most powerful tools and models in the AI space. In today's video, I'll be showcasing how to train the latest YOLO model YOLOv11 on a custom dataset. We'll not only walk through the training process but also dive into the accuracy obtained after training, review some of the key metrics generated, and explore the scripts used for this task step by step. By the end of this video, you'll have a clear understanding of how to fine-tune YOLOv11 for your own projects. Let's get started. The YOLOv11 model is developed by the Ultralytics team, and its source code is hosted on GitHub, making it easily accessible for developers and researchers. They have also provided extensive documentation on their website, along with highly detailed YouTube tutorials, making it easier to learn how to use this model effectively. In the top left picture, we can see the performance metrics of this latest YOLO model. It's evident that YOLOv11 is both faster and more accurate compared to its predecessors, a remarkable achievement in the field of object detection. On the right side, we observe that the YOLOv11 model comes in 5 versions: Nano, Small, Medium, Large, and Extra Large. These names correspond to the number of parameters in each model. As the number of parameters increases, the accuracy improves. However, this comes at the cost of reduced speed. This trade-off allows users to select the version that best suits their specific needs, balancing accuracy and speed for optimal performance. The YOLOv11 model is pre-trained on the widely used COCO dataset, short for Common Objects in Context, which includes 80 object classes across various categories such as animals, vehicles, sports, and more, as shown in the image displayed here. This dataset serves as a comprehensive benchmark in the object detection field, making it an excellent foundation for training models. The results we saw in the previous slide, showcasing the model's accuracy and performance, were achieved using this dataset. This highlights its robustness and credibility as a standard benchmark, enabling researchers and developers to measure and compare the effectiveness of different object detection models. For this tutorial, I'll be using my custom fire and smoke dataset, hosted on Roboflow, to fine-tune the YOLOv11 model. This dataset contains around 22,000 images across 3 classes: fire, smoke, and other. I introduced and detailed this dataset in my last video, so feel free to check that out if you're interested in learning more about its creation and structure. Additionally, this dataset has a dedicated GitHub page, where I've explained the entire process of creating it, from data collection to labeling and preparation. This resource provides a step-by-step guide for anyone looking to create similar datasets for their projects. All of this being said, let's dive into the code to see how I did the experiment. First, I want to mention that for this experiment I used a GitHub project I created called All YOLO Models that contains some scripts which facilitate the work with these models. The GitHub project and a snip with the video presentation for it are displayed in these images here. If you want to reproduce this tutorial, please clone my repo and let's get started. After I cloned the All YOLO Models repo, I have this PyCharm project that I renamed on my side with YOLOlib. See the background image. Here we have a downloadmodels.sh script which facilitates the model downloading. Running this script with a parameter, in this case YOLOv11, will download the code in the YOLO models directory, as you can see. We also have the option to reclone the model if we delete or change something in the original folder and errors appear, like we see I recloned it. Once we have the model, we can proceed to the next step, which is to download the fire and smoke dataset from Roboflow. These images demonstrate the manual process of downloading the fire dataset. Links to the Roboflow projects, along with information about the dataset splits, are provided on the GitHub page. By accessing one of these links, you will be redirected to the Roboflow Universe dataset page. There, you need to follow 9 steps, outlined here, to complete the dataset download. To simplify the process and avoid performing these steps manually, I created the download fire dataset.py script. This script accepts 2 arguments. the model for which you want to download the dataset, YOLOv11, and the path where the dataset will be downloaded. Once the script is executed, a YOLOv11 folder will be created at the specified location, containing all the images and labels for the dataset. With the dataset downloaded and prepared, we can proceed to the training task using the YOLOModelStrain.sh script, which internally calls the YOLO CLI from Ultralytics. The script requires three main parameters: the model and version to train, YOLOv11 version M, the number of epochs set to 100, and the batch size set to 48, the maximum supported by my GPU for this model version. These parameters were customized, while for others we use the default values set in the script, such as the task, detect, mode, train, data path specified by the dataset path variable in the parameters.yaml file, and model weights defined by the weights variable pointing to experimental results YOLOv11 weights. These are the key parameters required to execute the training task using the YOLO CLI. After executing the .sh script, the training process will begin. We can observe all the parameters used for the task, including those we did not configure, as the default values defined by the author are sufficient for most cases. However, in specific scenarios where the results are suboptimal, some of these parameters can be adjusted to potentially improve performance. For detailed information about these parameters, refer to the Ultralytics documentation, specifically the training section. Additionally, in the provided image, we can see the model's configuration, including the module names it comprises, the total number of layers, 409 in this case, and the total number of parameters, approximately 20 million. The training task is running on the RTX 4090 GPU, as previously mentioned, operating at full capacity with a batch size of 48. Both the training and validation images have been successfully processed without any errors, and the training process has started. After completing the first epoch of training and evaluation, we can estimate the total duration of the training process. Let's see how we can do this. The training time depends on the number of parameters in the model, the batch size used, and the GPU capacity. Batch size refers to the number of training examples processed in a single forward and backward pass. A larger batch size reduces the number of updates to the model parameters for a fixed dataset, as more data is processed in each step. This can lead to faster training in terms of wall clock time, as GPUs process larger batches efficiently due to parallelism. However, it requires more GPU memory to store the data and intermediate computations. In this particular example, training with 20,108 images and a batch size of 48 results in 419 steps per epoch, with one training epoch taking 2 minutes and 21 seconds. The evaluation step processes 4,757 images in 50 steps, requiring 14 seconds. The total duration for one epoch is 155 seconds. Over 100 epochs, this amounts to 15,500 seconds, which is equivalent to 4 hours, 18 minutes, and 20 seconds. This provides a rough estimate of the total training duration, though slight variations might occur due to factors such as GPU utilization and dataset complexity. Indeed, our calculations were quite accurate, as the actual training time turned out to be 4 hours, as seen in the image provided. The training process saved the results, including the trained weights, samples from the validation dataset, and evaluation metrics, into the experimental results YOLOv11 train folder. We will review these results shortly. After the training phase is complete, an evaluation is conducted on the validation dataset using the best weights saved for the model. The evaluation results are impressive, with a map for fire and smoke detection exceeding 90%, which demonstrates excellent performance. The normalized confusion matrix highlights that the model performs strongly in detecting fire and smoke, with accuracies of 90% and 89%, respectively, and moderately well in classifying other, with 81% accuracy. The background class serves as a reference for cases where the model predicts a class, e.g. fire or smoke, in the absence of any actual annotation for those classes. Misclassifications into the background class indicate false positives, where the model predicts fire or smoke, even though no fire or smoke is present. Specifically, fire is misclassified as background 9% of the time, and smoke is misclassified as background 30% of the time, suggesting these are common sources of false alarms. Similarly, other is misclassified as background 18% of the time. These results indicate that while the model effectively identifies fire and smoke in most cases, it occasionally struggles to differentiate between actual events and background noise, leading to false detections. Improving the model's ability to distinguish between true positives and background, possibly by enhancing features or adding more representative training data for edge cases, could significantly reduce these false positives and improve overall performance. Here, in this image, we have some graphics showcasing the training and validation performance metrics over 100 epochs for the YOLOv11 model, indicating steady improvement and convergence. The training losses, box loss, classification loss, and distribution focal loss consistently decrease, demonstrating that the model is learning effectively. Similarly, the validation losses follow a downward trend, although they remain slightly higher than the training losses, which suggests good generalization with minimal overfitting. Precision and recall metrics show a strong upward trajectory, stabilizing at high values above 0.8, indicating the model's ability to accurately detect and classify objects while minimizing false positives and false negatives. The mean average precision at 50% IOU threshold surpasses 0.9, showcasing excellent performance in object detection, while the stricter map at 50-95 metric steadily improves and stabilizes around 0.6, reflecting robust detection capabilities across a range of IOU thresholds. Overall, the metrics indicate a well-trained model that balances precision and recall effectively, demonstrating suitability for real-world deployment. In this slide, we have plotted two images that presents detection results from the YOLOv11 model, illustrating its capability to accurately identify fire, smoke, and other objects across a wide range of scenarios. Each detection is marked with a bounding box and a confidence score, which frequently exceeds 0.8 or 0.9, indicating the model's high reliability in its predictions. The model performs well in distinguishing between fire and smoke, even in challenging situations where both are present and overlapping within the same image. It also successfully detects other objects, such as vehicles or people, with moderate to high confidence. The examples span diverse contexts, including emergency scenes with firefighters, nighttime urban environments, and natural landscapes, showcasing the model's adaptability to different lighting and environmental conditions. These results highlight the YOLOv11 model's robustness and effectiveness, making it suitable for critical real-world applications such as fire detection, smoke monitoring, and emergency response systems where accurate and timely object detection is essential. All the results demonstrated in this video, including the trained weights, evaluation metrics, and examples of predictions, are publicly available on Google Drive. You are welcome to access them if you wish to use them in your own projects or experiments. With this, I wrap up the presentation. I hope it was informative and detailed enough to help you confidently train the YOLOv11 model on your specific dataset and analyze the results effectively. Best of luck with your YOLO projects. If you have any questions, suggestions, or feedback, please feel free to reach out to me via LinkedIn, email, or by leaving a comment on this video. Also, if you enjoyed this presentation, I'd appreciate it if you could support my work by liking this video and subscribing to my channel. Your support encourages me to keep pushing this work forward and continue improving it. Thank you for your time, and until the next video, stay safe and be curious to learn more. Goodbye.